Greetings from sunny San Francisco, and thanks for joining in on this online version of Physics 213. We're going to be covering Chapter 32 today. We'll be wrapping up Chapter 31 when I get back on Monday. There's some cool demos and concepts of resistance that we'll talk about then. But today we're going to work on basic circuit concepts. By the end of this chapter, there's some basic things you know. You should be able to understand and use Kirchhoff's loop law. You should know more about what an EMF is. We'll discuss power in a circuit, and we'll also discuss resistors in series and parallel, as well as resistor-capacitor circuits. First of all, let's just refresh our memory what Kirchhoff's loop law is. Here is a picture we saw several chapters ago. Notice we've got some equipotential surfaces, and if you start at point 1 and walk uphill 20 volts to point 2, we remember from a couple chapters ago that it doesn't matter what path you took. Likewise, if you were to start at point 1, take some path up to point 2, and then go round trip back to where you started, you're going to end up at the same potential energy at which you started, and therefore the net work done to go from point 1 to point 2 and then back to point 1 is going to be 0. And we did this in a very generalized potential field argument several chapters ago. Let's look at how specifically it holds in a circuit. We'll start with a basic circuit. Here is a circuit of 2 resistors with a battery in it. Remember, whenever you see the squiggly E, that stands for EMF, and EMF is just the way of saying the voltage of a battery. Some rules when we're dealing with loops of circuits are going to be that whenever we walk across a battery in the negative to positive direction, we call that a positive change in electrical potential energy. So as a charge walks uphill across a battery, it gains altitude, might be the way we think of it, or it gains an electric potential. And then the charge goes downhill when it crosses a resistor. In this case, we have 2 resistors, and so each resistor is going to give a potential drop until we drop back to the same potential at which we started. So the important relationship to realize is that the change in electric potential in a loop within a circuit always has to equal 0 joules per coulomb, or 0 volts. Let's see specifically what happens in the battery as electrons get to the battery. Here are some electrons traveling around a circuit. Notice that these electrons are going in the opposite direction of the current in the picture in which I drew. Remember that electron current goes in the opposite way that electricians like to define electrical current. Electrical current are imaginary positive charges that are going in the opposite direction that the negative electrons are really going. Sorry about that. Notice what happens as we increase the resistance. Well, maybe as not unexpectedly, the electrons slow down. So what a resistor does is it changes, it slows down the rate at which the electrons are traveling through the circuit. Now, as we increase the resistance, the current, the rate at the number of electrons that are going by per second goes up. Meanwhile, as we decrease the resistance, in this case, the rate is really going up. I think I said that backwards a second ago. As we increase resistance, the current goes down, and as we decrease resistance, the current goes up. And for a perfect resistor, that relationship is a proportional relationship. That the voltage is proportional to the current and proportional to the resistance, which means that for a given voltage, that the current is going to be inversely proportional to the resistance. Not all resistors follow this nice linear equation. As should be expected, the linearization is just a nice approximation, and it fits most resistors pretty good. However, many resistors change resistances as they heat up or cool down, or other properties of them change. For simplicity, we're just going to deal with these nice, perfect linear resistors. Now, in the last chapter, we looked at putting capacitors in series and parallel. We're going to do the same thing in this chapter. We're going to try looking at resistors in parallel and in series. Okay, here we see examples of resistors in series and resistors in parallel. Let's look what goes on in the case of resistors in parallel. Okay, here are 3 resistors ready to be set up in parallel. When we hook one of the resistors up, notice that electrons start flowing through the circuit. Now notice that the other 2 resistors aren't yet part of the circuit because they're just kind of dangling off on one side. Now I believe that all these resistors are 10 ohm resistors. Let's try hooking another one up. Okay, a question you might ask, is the current going to go up or down when we add this next resistor? Well, when we add it in, notice that the electrons now have another pathway to follow, so that the electrons as a whole, through the main branch of the circuit, is actually going faster once we add that new wire. And so the net effect is more current going through the circuit as a whole. And when we add that third resistor into parallel, we get more and more electrons. Now let's try changing the resistance in one of these resistors. If we decrease the resistance in that one resistor, notice the electrons are still flowing through it, but not as fast as they were. If we increase the resistance, let's make the decrease the resistance, increasing the conductivity. Let's make the resistance basically infinite. The resistance 0. Notice that the electrons go flying through at a very high speed now, and let's go all the way to 0. Notice that the electrons in the other resistors are basically negligible now. So when resistors are in parallel, the resistances add as an inverse, unlike the way capacitors did. In capacitors, the capacitance is added together here. In this way, the current can go through faster, so the net effect is a decrease in resistance as we put more and more resistors in parallel. Conversely, if we put resistors in series, now the electrons, they now have only one pathway to take, but each pathway they're bumping up against a resistor, which the net effect is that the total resistance is going to go up as a sum of all the individual resistances. So for resistors in series, the resistance goes up or increases as the sum of all the individual resistances. For resistors in parallel, the net effect is that the net resistance goes down because of the electrons have more pathways to take as they go through the circuit. Okay, now one more quick relationship is power. What is the power through a circuit? Well, something to remember is the units of power are joules per second. If you look at the units of electrical current, remember that electrical current are how many coulombs of charge go by per every second. a voltage is a joule per coulomb. So notice that when we take the current and multiply it by the voltage, that we end up getting joules per second. Power in a circuit is the current times the voltage. Note that when you pay your power bill, you are charged in units of kilowatt hours. Remember that a kilowatt hour is actually an energy and not a power. So it's really an energy bill you're paying when you pay your bill. Okay, I'm going to stop this here and download it. There'll be a second section on YouTube in a moment.